Hi friends, welcome to my channel Interesting Engineering. Let's discuss about current transformer. What's a current transformer? It's a type of instrument transformer which is meant for measuring large values of current even by using small range ammeters. It is used to extend the range of ammeters and it is also used in protection circuits. It acts as a step down transformer, that is, it reduces the current level from the input line to the range depending upon the range of the ammeter used in measuring. Now, let's discuss the circuit diagram and its what are all the errors that could occur in a current transformer. So first, as I said earlier, this is a type of instrument transformer for measuring current values. So normally what may be its working principle? Similar to any power transformer, this instrument transformer also works on principle of mutual induction. That is similar to a power transformer, it too has a primary and secondary winding, and based on the current flowing through the primary winding, there creates flux. So that flux links with the secondary winding and an EMF will be developed. So based on that principle, this current transformer also operates. So let's see about its diagram first. So here there will be a current line. So in this current line, the primary winding of the current transformer is connected in series with the supply line and it is connected in series with the load. So here this is the load and the current transformer's primary winding is connected over here, and to this primary winding we are connecting a secondary winding, and in the secondary winding we connect the meter that is meant for measuring the current value, and here this current is denoted by IP and this is the primary winding. So in the case of current transformer, the primary winding consists of single number of turn, so that there won't be any resistance, any huge resistance involved, so that it doesn't changes the circuit condition. So in order to reduce any such effects, we make use of single turn of wire in the primary winding, and in the secondary winding we have many number of turns, and the secondary winding is connected with the meter that is meant for measuring the current, and this primary is connected in series with the load. So the primary winding current is dependent upon the load and the secondary winding current depends upon the primary. So here let IP represents the current flowing through the primary, and this will be the voltage EP, and here the current through the secondary is denoted by IS. So normally in the case of current transformer, it is being earthed. So this earthing is provided to provide safety for the personnel operating with this instrument. So this is the current transformer diagram. So where we have two windings, primary winding and secondary winding. The number of turns in primary winding is denoted by N1 and the number of turns in secondary winding is denoted by N2, and here we have a single turn in the primary side and many number of turns in the secondary side, and in the secondary side we connect a ammeter for measuring the current through this instrumental current transformer. So this current transformer should always be earthed so that it provides safety to the personnel operating with this instrument. Current through the primary is denoted by IP and current through the secondary is denoted by IS. So in order to in order to analyze this circuit, analyze the operation of this instrument, that is to analyze the working of this current transformer, let me draw the equivalent circuit. So in the equivalent circuit there will be a resistance, that is RP, and here we have a inductance XP. So this inductance is connected with the primary. So this is the equivalent circuit, and here this is the secondary winding, and this secondary winding is connected with the resistance as well as the inductance. So this is the impedance of the secondary side, and this is the impedance of the load side. And apart from this, we have no load component denoted by IP, and so this is the equivalent circuit of a current transformer. So here we supply the input voltage, that is denoted by Vp, and this input voltage passes through the primary windings Rp and Xp. So this is the primary reactance, and here we have primary winding represented. The voltage developed across the primary winding is denoted by Ep, and the voltage developed across the secondary winding is denoted by Es, and here we have the reactance at the secondary side denoted by Rs and Xs, and this is RL, XL. So this is the equivalent circuit of the current transformer, and apart from this, here we have IS, the IP. This is the primary current flowing through the based on the supply given here, there flows primary current. This primary current enters through these reactance terms, and here we have primary winding, and the voltage developed across the primary winding is denoted by Ep, and when no load is being connected over here, the flows current, that is represented by I0, which is nothing but the no load current, and here we have IC as well as IM current flowing through these two components. The current flowing through the resistance under no load condition is denoted by IC, that is the core loss component, and this is the magnetizing component IM, and I0 represents the no load current. And apart from this, here we have IS. IS is nothing but the secondary current that flows through this entire circuit, and the voltage developed across the load terminal is denoted by Vs, which is nothing but secondary terminal voltage. So this is our equivalent diagram of the current transformer. So this current transformer diagram, I have drawn the equivalent circuit for this entire structure. So this is the equivalent circuit of the current transformer, where we have primary and secondary winding. So due to the current flowing through the primary winding, that creates flux phi. So this phi develops voltage Ep, and based on the mutual inductance concept, there develops voltage in the secondary denoted by Es, and due to the current flowing through the primary is denoted by Ip, and current flowing through the secondary is denoted by Is, and under no load condition, the current is denoted by I0. The current through this terminal is called the core loss component of current, and the current through this terminal is called the magnetizing component of under no load condition. So this is our equivalent circuit, and based on this equivalent circuit, let's draw the phasor diagram. So while drawing the phasor diagram, I am going to consider the flux term first. So this is our flux phi. So I am representing this flux phi. So here we have flux. So due to the current, input current, we have flux phi, and this phi is being represented here. So this flux phi, and due to the flux phi, there develops voltage in the primary winding. So I am going to represent the primary winding voltage here. So this is Ep. So this is the primary winding voltage, and due to mutual induction principle, there develops potential in the secondary, which is 180 degree out of phase with the primary winding. So due to the current flowing through the primary winding, there develops flux. This flux creates a potential EP, and due to the mutual induction, there develops potential in secondary. So that is denoted by ES, and EP and ES is 180 degree out of phase. So I have represented like this. And then we have, under no load condition, we have IC and IM. So this IC current is the current flowing through the resistance. So look at the equivalent circuit here. So the IC is nothing but the current through the resistor. So this current will always be in phase with EP. So I am representing here, and IM is flowing through the inductor. So it will have a phase difference of 90 degrees. So I am representing IM over here. So this is IC and IM. So the net component of IC and IM will be I0. This is the no load current. And then we have, due to this IC and IM, we have I0, and apart from this I0 makes an angle of alpha with the phi axis. Then we need to represent the secondary current. So due to the voltage developed in the secondary, there flows current IS through secondary line. So this secondary line will have a reactance component. So this current lags behind the voltage by certain angle delta. So I am representing it here. So this is IS, and it has an angle of delta, and this IS have an angle of delta, and this IS, when extends through the primary side, we can represent it by NIS, because we have in current transformer, turns ratio is equal to I1 by I2, that is nothing but IP by IS. So this IP, we can write it as IP is equal to N into IS. So I am drawing this IP as N into IS over here. So this is IS line, and when we extend it through the primary side, we have NIS. So I have represented this here, and then if we see here, IP is nothing but I0 plus N into IS. We have IP here. This IP line gets divided into two branches, I0 and NIS. So I am drawing this IP as the sum of these two. The net component will be IP. So here we have IP, and this angle, here we have delta, here we have alpha. So here this angle will be 90 minus delta minus alpha. So look at our phasor diagram. So in our phasor diagram, we have represented flux, and due to this flux there develops EMF EP, and due to this EMF EP there develops potential ES, which is 180 degree out of phase, and due to this ES there flows current. So this current will have a lagging power factor. So IS, I am representing it here with an angle of delta. So this IS due to IP is equal to NIS, I am representing here. So when we extend it to the primary side, we can mark it as NIS, and this NIS plus I naught gives you IP. So the combination gives IP, and this angle, since here this is delta, the angle between ES and IS is delta, so I am representing the same angle over here, delta. So the angle between EP and NIS is nothing but delta, and the combination of NIS and I naught gives IP. So the angle between these two will be 90 minus delta minus alpha. So the entire angle is 90 degree. Here we have alpha, here we have delta. So this angle will be 90 minus delta minus alpha. So this is about our phasor diagram, and apart from that we need to represent this Vs and ISRS and ISXs. These things we have to represent. So let me represent it here. So due to the flow of current IS, this IS flows through RL and XL component. So there develops a terminal voltage Vs. So this Vs I can represent it here. So Vs is represented here. Vs, and then apart from Vs we have ISRS and ISXs. So since this ISRS, this IS flows through RS, the potential will be in phase. So it will be in phase with this IS. So I am representing here. So this is ISRS, and then we have ISXs. So since this is through inductor, there will be a phase difference of 90 degree. So this ISRS is in phase and ISXs will be here. So ISXs, when we join these, we have ES. So this is our phasor diagram. So could you all understand this? The first thing, we have flux. Due to this flux we have EMF EP, and this due to this EMF EP there develops a potential in secondary denoted by ES, and this will be 180 degree out of phase. And this ES, due to the ES there flows current IS, so there will be a phase difference of delta, and due to this IS, when this IS is extended over the primary side, we represent it as NIS, and this NIS we can have it as when we combine this NIS, here we have NIS, here we have I naught. So the combination of NIS and I naught will be IP. So I have joined this line. So we have IP line here, and apart from this I am representing Vs, ISRS and ISXs. So here we have Vs, ISRS, ISXs, that I have represented here. So due to the potential ES and IS, there develops a terminal voltage Vs, that is represented here, and this when this secondary current flows through the resistor, there will be the potential will be in phase with IS, so ISRS, and due to the flow of current through Xs, there will be a phase difference of 90 degrees. So I have represented here. So it is ISXs, and the combination of Vs plus ISRS plus ISXs will be ES. So I have joined with this. So this is our phasor diagram. So to derive at our equation for phase angle error and the ratio error, we need to we need to explain with this phasor diagram. So we should be clear with the phasor diagram first. So we have drawn the phasor diagram. So with this phasor diagram, we need to explain about the two different types of errors that could occur in a current transformer. So to derive at the expression for ratio error and phase angle error, I am going to consider only this quadrant of the phasor diagram. Okay, so I'm going to consider only this portion of phasor diagram to derive at the expression for ratio error and phase angle error. In an ideal current transformer, the ratio error, the ratio should always be equal. That is, n should be equal to I1 by I2. But there will be some sort of deviation occurring in this current transformer. So what sort of deviation that will be occurring, that let's discuss with the expression for it. So to derive at that expression, I am going to consider only this quadrant. So once again I am going to draw the phasor diagram considering only the first quadrant. So in the first quadrant we have phi, and here we have Im, and here we have EP, then we have IC. The combination of IC and Im will be I0. So here we have NIS, and then we have IP. So this makes angle alpha, this makes an angle delta, and the angle between these two will be 90 minus alpha minus delta. So with this portion we are going to consider, we are going to derive at the expression for ratio error. So for that purpose I am going to extend this, name these lines first. So this point I am going to name it as O, and then here I am going to name it as C. This point is named as A, and I am going to extend this A point at the top so that it makes an angle of 90 degree with it. So this is 90 degree line. So this point I am naming it as B. So with this portion I am going to consider the certain angles so that I could derive at the expression for ratio error. So here the OA line is extended so that the C point touches over the extended OA line, so that we could have a 90 degree angle there. So here, since here we have 90 minus alpha minus delta, the same angle will be subtended over here. So for our simplification purpose, for our clarity purpose, now I am going to take only this portion and draw it over here. So when we consider this angle, this triangle OCB, I am going to consider OBC triangle. So I am drawing it separately now. So this is C point, this is O, this is B, and from C I am having a point A. So from our diagram, look here. So what is OA? OA is nothing but it is a line representing NIS. So I am naming it as NIS. And then OC, this is a IP line. So I am naming it as IP. And then we have angles. This B angle is 90 degree, and this angle will be 90 minus alpha minus delta. And apart from that, this AC line, here we have IO. So the same thing will be taken here. So this line will be I naught, that is AC line is nothing but I naught line. So from this triangle I am going to derive at certain equations. So first we have drawn the phasor diagram, and from that phasor diagram we are considering only the first quadrant, and I'm simplifying. Diagram is drawn here. So from this diagram I'm considering only this triangle portion, and it is drawn over here. So based on this triangle, now I am going to derive the equation for ratio error. So here first let's consider, I am going to take this triangle first. So in our triangle ABC, first let's consider the triangle ABC. So in triangle ABC, what is sine theta? Sine of 90 minus alpha minus delta is equal to, this is angle portion. So for this angle, what is sine angle? Sine angle 90 minus alpha minus delta will be opposite side by hypotenuse. Opposite side is nothing but BC. So it is BC divided by hypotenuse is nothing but I naught. So here it is I naught. Sine of 90 minus alpha plus delta is equal to BC by I naught. So sine 90 minus theta will be sine 90 minus theta will be cos theta. So cos of alpha plus delta will be equal to BC by I naught. So BC is equal to I naught cos of alpha plus delta. So BC is equal to I naught cos of alpha plus delta. And then when we consider cos 90 minus alpha minus delta is equal to, for this angle cos theta will be adjacent side by hypotenuse. Adjacent side is nothing but AB. AB by hypotenuse is nothing but AC, which is nothing but I naught. So AB by I naught. In here also, cos of 90 minus of alpha plus delta is equal to AB by I naught. So cos 90 minus theta will be sin theta. So sin alpha plus delta is equal to AB by I naught. So AB is equal to I naught sin of alpha plus delta. So we are going to make use of these two terms in our derivation purpose. So I have taken a particular portion from the phasor diagram. So with this triangle we have derived the equation for sin theta and cos theta, and then we are going to consider this entire triangle. So for this entire triangle OBC, we make use of Pythagoras theorem. So by using Pythagoras theorem, OC square is equal to OB square plus BC square. So OC is nothing but, from our diagram, OC is nothing but IP. So OC is nothing but IP square is equal to OB. Look at our diagram. In OB is nothing but OA plus AB. So I write it as OA plus AB the whole square plus BC. BC square is nothing but BC square. So here IP square is equal to OA. What is OA? Look at our diagram. OA is nothing but OA. So this OA is nothing but NIS. So NIS plus What is AB? We have derived AB is equal to I naught sine of alpha plus delta. So in the place of AB, I am replacing it as I naught sine of alpha plus delta the whole square plus what is BC? Here we have BC square. So we have derived what is BC. BC is nothing but I naught cos of alpha plus delta. So I naught cos of alpha plus delta the whole square. So when we expand, so look at our equation. So in this equation, it's of the form a plus b the whole square. So in our equation, we have a plus b the whole square. A plus b the whole square is nothing but a square plus 2 into nis into I naught sine of alpha plus delta plus b square. B square is nothing but I naught square sine square alpha plus delta plus I naught square cos square alpha plus delta. So here we have n square I square plus 2n is I naught sine of alpha plus delta plus in these two equation we have I square common, I naught square common, taking it outside, sine square alpha plus delta plus cos square alpha plus delta. So n square is square plus 2n is I naught sine of alpha plus delta plus I naught square, because sine square theta plus cos square theta will be 1, so I am replacing it by 1. So we have only I naught square. So we have IP square equal to n square is square plus 2n is I naught sine of alpha plus delta plus I naught square. So when we introduce sine of alpha plus delta here, I naught will be very much less than nis. So when we add I naught sine of alpha plus delta, it will be negligible. So here I am adding n square is square plus 2n is I naught sine of alpha plus delta plus I naught square sine square alpha plus delta. So here it looks like a square plus 2a into b plus b square. So we can write it as a plus b the whole square. IP square is equal to nis plus I naught sine of alpha plus delta the whole square. So IP will be nothing but nis plus I naught sine of alpha plus delta. So this is our IP equation. So what is ratio error? Ratio error is nothing but Kn is equal to IP by Is. So what is IP? We have derived nis plus I naught sine of alpha plus delta divided by Is. So it is n plus I naught sine of a plus b will be sine a cos b plus cos a sin b divided by is. So when we look at our diagram, so here when we look at our diagram, take this triangle, consider this portion. So here when we take sine alpha is equal to opposite side is nothing but IC by IM. Sine alpha will be IC by IM. Sine alpha will be IC by I naught. Opposite side by hypotenuse will be I naught. So IC is equal to I naught sine alpha. And in this triangle, what is cos alpha? Cos alpha will be equal to adjacent side by hypotenuse, which is nothing but IM by I naught. So taking this to the other side, IM is equal to I naught cos alpha. So here from this small triangle we have obtained the equation for sine alpha and cos alpha. So from that I have obtained IC equal to I naught sine alpha and IM is equal to I naught cos alpha. So based on this, now let's see. So here n plus I naught sine alpha cos delta plus I naught cos alpha sine delta divided by is. So what is I naught sine alpha? I naught sine alpha will be IC, whereas I naught cos alpha will be IM. So I am replacing here. So Kn is equal to n plus IC cos delta plus IM sin delta by is. So when we look here, when we substitute, when delta is very much less than 1, substitute delta very much less than 90 degree. So cos 90 will be 1, sin 90 will be 0. So when we can eliminate this entire term, so Kn will be equal to n plus IC cos IC by is. So we could obtain Kn is equal to n plus IC by is. In general, the ratio should be K is equal to n. For an ideal transformer, the ratio should always be equal to n, whereas here we obtain it as Kn is equal to n plus IC by is, which is nothing but in the case in a practical current transformer, the ratio error depends upon the core loss component of under no load condition. Apart from the ratio, we have core loss component also. So that affects the ratio of a current transformer. So under no load condition, the core loss component affects a current transformer. So that is the major cause for causing a ratio error in the case of current transformer. Then we shall discuss about the phase angle error. So in the case of phase angle error, so in our triangle, I am going to find out what is tan theta is equal to opposite side by adjacent side. What is opposite side? So here this theta I am considering. So what is tan theta? Opposite side by adjacent side. So opposite side is BC and adjacent side is OB. So here BC divided by OB is nothing but OA plus AB. So OA plus AB. So what is BC? BC is nothing but I naught cos of alpha plus delta. So I naught cos of alpha plus delta divided by what is OA? OA is nothing but NIS. NIS plus AB. AB is nothing but what is AB? AB is I naught sine of alpha plus delta. So I naught sine of alpha plus delta. So here we shall find out. So compared to NIS will be very much greater than I naught sine of alpha plus delta. So I am eliminating this term. So it changes as I naught cos of alpha plus delta divided by NIS. And apart from that, when we expand this cos A plus B will be cos A cos B minus sin A sin B divided by NIS. So it is I naught cos alpha cos delta minus I naught sin alpha sin delta divided by NIS. So what is I naught cos alpha? We have find out I naught cos alpha is nothing but Im. So theta is equal to Im cos delta minus what is I naught sin alpha? I naught sin alpha is IC. So I am replacing here IC sin delta divided by N into IS. So for when delta is very much less than 90 degree, when delta is less than or equal to 90 degree, when delta is 0, very small value, delta is of small value, sin 0 will be 0, cos 0 will be 1. So we can write it as theta is equal to Im by NIS. So the phase angle error occurs due to the magnetizing component of the current, magnetizing component of no load condition, whereas the ratio error is due to the core loss component. So let me summarize. So a current transformer reduces the current level to a smaller value so that we can able to measure even with a small range ammeter. At any condition, the secondary of the current transformer should always be short circuited, and it should also be insulated so that it doesn't cause any damage to the personnel operating in the environment. And we have drawn the equivalent circuit. From this equivalent circuit I have drawn the phasor diagram. So to derive the expression for phase angle error and ratio error, we have considered the first quadrant in our derivation purpose. So with this first quadrant, we are considering only the particular triangle portion. So I have drawn it separately. So from this triangle we have found out what is IC, what is IM, what is AB and what is BC. Based on these terms we have derived the expression for ratio error, that is Kn. So Kn should always be equal to N, which is nothing but the ratio, which is I1 by I2, that is IP by IS. But in this practically in a current transformer, Kn will not be equal to N but will be dependent upon the core loss component of the transformer. So whereas the phase angle should always be the secondary current extended to the primary side should always be equal, that is this NIS component and the IP component should not have any phase difference. This NIS and IP should not have any phase difference. Practically in a current transformer there exists some sort of phase difference theta. So that theta we are deriving using these equations, and that theta we have it as Im by NIS. So that theta is dependent upon the magnetizing component of the current transformer under no load condition. So these are the two factors that could cause error in a current transformer. So in order to avoid such errors, we should carefully design the current transformer so that there occurs the minimum amount of error in our operating time. So this is about the current transformer. In our forthcoming video, we shall discuss about potential transformer. For more videos, keep watching. Please subscribe and share. Thanks for watching.